Hello everyone, welcome to the PUFacademy lecture. In this chapter, we're going to introduce NIST Special Publication 800-22, a classic suite of tests designed to check whether a bit stream truly has random characteristics. Starting from some key concepts of randomness as presented here on the slide. This topic is fundamental in many areas, especially in computer science and security. Here we divide the randomness tree into two parts. One is the properties of randomness, and the other is the randomness of a sequence. First, let's look at the basic properties of randomness. There are two core ideas here. The first is independency. This is easy to understand. Think of a coin flip. The result of the next flip is absolutely not affected by the result of the current flip. They are independent events. The second property is unpredictability. Simply put, if you don't know the starting point, often called the seed, you should not be able to guess the resulting values or sequence. Next, we look at what makes a whole sequence truly random. A good random sequence must have uniformity. This means that when you look at all the possible outcomes, they should be equally likely. For example, in a truly random sequence of numbers from 1 to 10, the number 7 should appear almost equal to the number 3. Then there is scalability. This simply means that if you take a smaller part or a subset of a longer random sequence, that smaller part must also be random. Finally, we have consistency. This is particularly important for generating randomness. It means that the output should maintain its random quality across all possible starting seeds. Now you might be curious, where does the randomness come from? Randomness can be generated from PRNG or TRNG. The differences you can think as below. As the name suggests, these generators don't produce true randomness. Instead, they use a mathematical function f of seed to generate an arbitrarily long sequence. The entire sequence is determined by the initial seed value. There are two main characteristics of these sequences. First, they are periodic over a certain number of iterations. Because they are deterministic, the sequence will eventually repeat itself. Second, they are equidistributed up to a certain number of dimensions. This means that, statistically, the values are evenly spread out, which helps them look random. Now let's compare them with TRNGs, or true random number generators. Good entropy sources, which is the source of true randomness, are typically physical. They rely on unpredictable real-world phenomena, like atmospheric noise or radioactive decay. This leads to a key relationship. PRNGs need TRNGs to provide their seeds. A pseudo-random sequence can only be as unpredictable as the true random seed it starts with. While PRNGs are not truly random, they have a major advantage. PRNGs are faster in terms of generating large sequences compared to TRNGs, which rely on slow physical processes. So how to evaluate your randomness? Let's look at the NIST SP 800-22, which is a statistical test suite for evaluating the randomness of number generators used in cryptographic applications. On the left, we see the comprehensive list of test items included in the suite. There are quite a number of them designed to check randomness from various angles. They range from basic tests like the frequency monobit test and the runs test, which check for the balance and distribution of bits, to more complex statistical analysis like the binary matrix rank test, discrete Fourier transform, spectral test, and the linear complexity test. The suite also includes tests for recognizing patterns, such as the non-overlapping and overlapping template matching tests, and tests that look at predictability like the Moore's universal statistical test and approximate entropy test. For each one of these tests, the right side details the specific information provided. Every test item has a clear test purpose and specifies the function call for implementation. It defines the core mathematical components, like the test statistic and reference distribution. It also includes the detailed test description, the decision rule, typically set at the 1% significance level, and guidance on the conclusion and interpretation of results. Besides, it gives an input size recommendation for the bit sequence being tested and provides an example. So this suite offers a standardized, rigorous method for statistical validation of random and pseudo-random number generators. Now let's look at an example of one of the NIST tests, the cumulative sums test. The hypothesis of this test is straightforward. It checks if a series of random walks shows a clear, non-random tendency. If the sequence is truly random, the walk should not drift too far from the starting point. The specific version shown here is the forward cumulative sums test. To perform this, we first establish some notations. We convert the binary input, the zeros and ones, into a new variable. Let's call it x sub k. We calculate this x sub k by taking 2 times the bit value and subtracting 1. For example, if a bit is 0, x sub k becomes -1. If the bit is 1, x sub k becomes +1. Next, we calculate the statistics, specifically the partial sums. The partial sum, s sub k, is calculated by taking the previous partial sum, s sub k minus 1, and adding the current x sub k value. As an example, if we have a sequence of 5 bits 10110, the partial sums will change as we move through the sequence 10121. Finally, we determine the test statistic. This value, z, is the maximum absolute value of all the partial sums calculated during the entire sequence. In our example, the test statistic z would be the maximum among those, which is 2. The final result, z, is then used to determine if the sequence is sufficiently random, based on the maximum excursion of the random walk. Continuing with the cumulative sums test, let's look at how we get to the final decision using the p-value. The slide shows a long and complex formula for calculating the p-value. Essentially, the p-value is determined by a series of sums that involve the Gaussian cumulative distribution function, or phi, applied to various terms related to our test statistic z, the sequence length n, and the square root of n. This p-value is derived from a theoretical model that tells us the probability of seeing a sequence as extreme as the one we observed, assuming the data is truly random. Once we have the p-value, we apply the rejection region rule. If the calculated p-value is less than the predetermined significance level, usually 0.01 or 1%, we reject the null hypothesis, denoted as H0. Rejecting the null hypothesis means we conclude that the sequence is not random. The result has clear implications based on the test statistics we found earlier. A large z-value implies that there were too many zeros or ones clustered together, especially at the early stages of the sequence, if we are running the forward test. This indicates a definite non-random trend. Conversely, a small z-value is also problematic. It implies that the zeros and ones are intermixed too evenly, which can also be a sign of a non-random, deliberately structured sequence. Finally, the recommended n, the length of the bit sequence we input, should be at least 100 for the test to be statistically valid. This slide shows the mathematical details regarding the results of the cumulative sums test. The first point is how the p-value is determined. The p-value is derived from the limiting distribution of the test statistic z, which, as we discussed, is the maximum absolute value of the partial sums. This is the theoretical basis that allows us to interpret our test results statistically. The main takeaway from this test is the implication of failure. A failure to pass the forward cumulative sums test typically implies an uneven distribution of zeros, or ones at the early stages of the sequence. This means the sequence shows a bias like a significant run of ones right at the beginning. Now, it's important to understand the effect of where the imbalance occurs. If an uneven distribution of 0 or 1 appears at a late stage of the sequence, the test statistic z will still be small. This is because the earlier, balanced sums prevent the maximum excursion from becoming too large. We have a couple of examples to illustrate this. In the first example, a sequence like 1010010001010111111, the test statistic z is only 3. This low number suggests a strong balance despite the long run of ones at the end. In the second example, 11111101010001001, the test statistic z is 6. This higher value is due to the clustering of ones at the beginning of the sequence, demonstrating that the test is most sensitive to imbalances that occur early on. This highlights the test's specific strength in detecting initial bias in a bit stream. Let's see an example for the NIST 800-22 test. This table is an extremely positive example, showing the results of testing a device called the NEO-PUF, using the rigorous NIST statistical test suite. This result demonstrates what a statistically perfect random number generator looks like. We see the output sequence was subjected to 16 different statistical tests, from the simple frequency test to the complex linear complexity test. Notice the required input size for some of the more advanced tests is as high as 1 million bits, showing the robustness of the evaluation. Now let's look at what the key parameters mean, as they all align perfectly here. The columns under the decision rule are crucial. The P/F proportion tells us how many individual subtests pass the p-value criteria. In nearly every case here, we see a ratio like 73 out of 75, or 3 out of 3, indicating a near-perfect success rate across all checks. The next column, uniformity, checks that the resulting p-values are themselves evenly distributed. For a truly random source, the p-value should also be uniform, and here they consistently pass this check. For example, for the block frequency test, the value is 0.72554. For the cumulative sums forward test, it's 0.519816. And for the spectral DFT test, it's 0.937294. These p-value uniformity numbers are all well above the typical required significance level, often set very low like 0.0001. These non-extreme p-value uniformity results, none of them near 0 or 1, statistically confirm that the p-values themselves are not biased, thus demonstrating the uniformity of the distribution of p-values. Finally, the randomness check column is the ultimate indicator, because all parameters met the strict statistical standards. Every single test item shows a definitive pass. Use this example of table. Hope you can know how to evaluate your product's randomness. Thank you for watching PUFacademy lecture. We look forward to seeing you again soon.